All right. Hello, everyone. So my name is Ravi Sahita. I work at Intel in the data platforms group, and my co-speaker is Samuel Ortiz. I'll let him introduce himself. So we'll talk about confidential containers in public clouds. The talk is sort of split into two parts. Given the amount of time we have, about 25 minutes or so, we'll sort of it's more of like a lightning talk because obviously 25 minutes is not sufficient for some of the depth we can go into these topics. So we'll cover in the first half of the talk, we'll focus on the TDX architecture, give you a sort of a quick overview on some of the key points of the architecture, and then Samuel in the second half will focus on the container aspects, and the software touch points and you know uh, required things that we need to do in the open source environment, right? With that, let's get going. I covered the topic sort of already, so I'll just jump into it. So in terms of the cloud threat vectors, right, there are three sort of areas that are motivating confidential computing, right? And I think I'm preaching to the choir here, so I'll run through this quickly, right? One is sort of the misuse or the attack surface exposed in the cloud, right? The second is privacy, right? And cloud providers want to also be able to extract themselves from the TCP of the tenant data, right, from a privacy perspective, and also flexibility, which leads to also a complex attack surface, right, is to be able to support different kinds of isolation models like application enclaves, VM enclaves, containers as workloads and microservices in the future as well, right? So this leads to sort of a complex landscape of software and hardware within which confidential computing has to be implemented. So if you look at the evolution from a workload isolation perspective, right, that Intel has gone through, for example, um, is sort of gone through this track, right? We've had hardware virtualization for a while. We've introduced capabilities that hardware virtualization can use to encrypt memory on the platform, but both of those first steps keep the VMM and the host software. I'm sort of using VMM as a general term to include all of the host software, QMU, the hypervisor, KVM, etc. They all and the other cloud services, they all stay in the TCP. With SGX and TDX, we sort of have these capabilities that allow you to remove these host software capabilities from the TCP, right? In a systematic manner, right? With SGX, the goal is to sort of focus the trusted execution environment on the app, and that may require app refactoring or may require library OSs. With TDX, which we're talking more about today, the goal is to similarly remove the host software environment from the TCP with with sort of a balance in terms of keeping the guest VM as the definition of the trusted execution container, right? And that leads to enabling that we need to do in terms of the VMM, the OSs, the host software environments, as well as some of the guest OS environments. But once we are done with that, two or three major VMMs and OSs that we need to support, we can essentially bring in a lot of the applications, container workloads without any changes, right? So that's sort of the design point we're trying to hit with Intel TDX. So I touched upon the security goal of the architecture, but let's also look at some of the non-goals, right? So we want to maintain the role from a cloud service provider perspective. We want to maintain the role of the VMM, right? That remains the control point in the cloud, ensuring the availability of these of the cloud VMs and managing and arbitrating resources between them. And so therefore, we also want to make sure that while we are supporting these confidential VM models, we ensure that those confidential VMs don't, are not a vector of, causing any sort of privilege escalation for the host software. Some things that are out of scope for TDX and for most of these sort of trusted execution environments, right, are to sort of prevent any sort of denial of service from the host environment. The host environment, the VMMs, etc., remain in full control on the platform. And also in terms of TDX specifically, preventing some of the advanced hardware adversary attacks are out of scope in some of the initial generations. We do address some of the simpler hardware adversary attacks with TDX, and I'll touch upon that in a little bit more detail. So with those security goals in mind, let's just look at quickly the core aspects of the architecture, right? So the first thing for supporting TDX, we introduce a CPU mode called SEAM, or Secure Arbitration Mode, and that essentially allows us to host a TDX module. So the TDX module is a core TCP element of TDX. Think of it as a firmware software element, right? It's loaded through an Intel ACM, right, which allows us to essentially extend the measurement of this specific TDX module loaded on the platform into the CPU, right? And that can be then reported later on to support the attestation models. We obviously talked a lot about attestation and its importance for trusted execution today. The TDX module is also protected in physical memory against software accesses of all kinds, as well as has memory confidentiality and integrity support against some of the simple hardware adversary attacks. So as we introduce this secure arbitration mode, along with that, there are a few instructions introduced that allow the host software to manage this notion of TDs, right? So the TDs, for all intents and purposes, are confidential VMs. So they're managed. We want to maintain the look and feel of how these are managed by the VMM and the host software, and that's done through these set of intrinsics introduced that you see in the horizontal interface called SEAM call and SEAM ret. And those are essentially like, gateway interfaces to invoke a set of intrinsics that the TDX module hosts for the VMM in order to manage TDs, right? At the same time, the TDs also may require services of the host, like paravirtualized IO, for example, and those are achieved through a set of vertical interfaces that you see here called TD call, right? The VM exit, VM entry flows that are shown here are pretty much similar to what we have with the hardware virtualization. There is also a new intrinsics exposed to the TDX module itself and is restricted to the privilege of that SEAM mode of operation, which is used to support some of the attestation flows. So that's sort of one of the key cornerstone elements of the TDX architecture. So if you look at how this capability is then used to hold together, to put together some of the security objectives of the architecture, we leverage the memory encryption engine that is introduced as part of TDX, and which SGX also leverages, right, for memory confidentiality and integrity. And that is used by the TDX module in order to manage the lifecycle of keys, the unique ephemeral keys assigned to the TDs. And that's what I'm showing here as this private key assigned to a TD, right? And in TDX, the namespace of those key IDs is separated at initialization time and locked down by the CPU firmware, so that the lifecycle of TDX keys can be managed through the TDX module, whereas the lifecycle of the legacy VM keys can continue to be managed by the VMM. Once that lifecycle management of the keys is in place, right, and a private key ID can be securely used by a TD, the hardware then enforces this notion of separating the TD's use of memory into private memory and shared memory. What private memory used by the TD implies is that for some of these critical actions like page walks and code fetches, those access are always held in TD private memory, right? That's sort of a grounding rule in the architecture. Beyond that, the TD can choose to use what data it accesses it hosts itself in private memory, and what data it chooses to expose to the VMM for paravirtualized IO and things like that through shared memory, right? Um, Along with that, then let's talk a little bit about confidentiality and integrity. So confidentiality is a property and integrity is a property enforced by the memory controller, right? And that's the use of the ephemeral unique key that is never visible to software, right, as part of those TD's accesses to memory. While that's happening, memory integrity capabilities are in place as well, so that any malicious tamper by software, the untrusted software, disallows a TD from consuming that data, right? And that is shown here on the right, where you see this like MAC failure occurring on the reads. And if the accesses is correctly performed by the TD, those message and authentication codes are updated on the and carried and maintained with the metadata associated with that memory. And what you can see on the left is any untrusted host accesses to that memory are essentially prevented, including accesses to ciphertext, right? So we want to prevent access from the VMM or the host software from trying to access ciphertext and perform dictionary attacks, for example. And any writes or malicious accesses through alternate key IDs essentially corrupt the integrity information on memory so that the TD can't consume it and can't execute incorrect code. So let's look. So with that, so we've sort of seen the first layer, right? There's a TDX module. We've seen the second layer of key management and how the memory confidentiality and integrity is used. Let's look at how that building block is now applied to protect the runtime of the TD itself, right? So on the left hand side, you can see the runtime state of the TD. As I mentioned, in TDX, we leverage the sort of the well-tested virtualization extensions, and the control structures and the runtime state of the TD is essentially protected by using the TD's ephemeral key, right? And that prevents any runtime tamper of those control structures or data structures, including virtual CPU runtime state by the VMM, right? The other advantage of this model also is that it lets us scale the use of memory on the host for TDs, in a very uniform manner, right? Without any limitations of any restricted memory. The same concept is also used to extend the second level paging structure, right? So as you recall, in virtualization and therefore also in TDX, each TD is running as a VM, so its memory is accessed through a nested walk, right? So a linear address in the guest kernel inside the TD is translated to a host physical in a recursive walk going through the IA paging structures and the second level paging structures, right? And the second level paging structures are known to the host, right? But we want to make sure those nested paging structures are not accessible in the way that remapping attacks have to be prevented, right? Achieved through this concept of a secure extended page table. It's a second level paging structure that's protected with the ephemeral key of the TD, thus preventing, because of memory integrity checks, preventing any tamper of those data structures, right? And as you can see here, a private access, therefore, by a TD essentially remains, the page walk remains in private memory space, and then culminates in the memory controller using the key ID assigned to that TD, right? And the other concept this slide is trying to show is that shared memory accesses essentially follow the same legacy model that we have, right? That they would be transferred through the secure EPT, the shared EPT page table structures shown here, managed by the VMM, and would allow the VMM to essentially manage that accessible memory, just like legacy. So with those two concepts in place, let's just touch a little bit upon the threat model. Like we said, we've talked a lot about attestation, so it makes sense to sort of just baseline on the TDX TCB and threat model. So the core elements of the TCB are the TDX module, right? And obviously, in addition to the CPU hardware and microcode, we also use an ECM to bootstrap the TDX module right into the range register protected region. And finally, we leverage a lot of the work that the community and Intel has already done in terms of the attestation infrastructure using a coding enclave, right? So people who are familiar with the coding model and code generation model of enclave can think of applying that to TDX pretty much as is, with some very important changes. One important change is a TD beyond its static measurements also supports the notion of runtime measurements, and that is to give flexibility to the software so that if you're loading a container runtime, or if you're loading some specific application inside the TD, you have the ability to dynamically also measure those components as the TD starts executing, and that's reported as part of the code generated eventually for the TD. For folks who are familiar with the attestation flow, this should look very familiar to the SGX attestation model, right? With the only subtle difference is that the way the local MAC report is generated for the TD is through a TD call, right? Which essentially in turn is hosted by the TDX module, which in turn uses the CMOPS instruction to essentially generate a CPU MAC report, right? Which includes its measurements, the TDX module measurements, and the TD's measurement that the TDX module is hosting. And that's converted to a code through a coding enclave that's hosted elsewhere, but on the same physical platform. And then that can be provided to the challenger, right, or relying party that can use the attestation verification flows to essentially verify that the following hierarchy is correct, right? That this is a valid code from a attestation signature that has been that is rooted in a PCK certificate that belongs to Intel, right, or is signed by Intel rather. And that proves the property that it is a TDX authenticated platform with a specific TDX module and a specific TD measurements that the relying party chooses to trust. So before I switch over to the container side that Samuel can go through, I just wanted to touch upon. So the goal behind building TDX is to provide this flexible unit of compute that obviously applies to the virtualization models with VMs, can map over to the container models as well, and Samuel will go into that in depth, right? And can also extend to other function as a service models with the right amount of enabling at the system software layer, right, without having to modify any of the containers or applications themselves, right? So with that, I'll hand over to Samuel so he can jump, take us more through the container flows.
Thanks, Ravi. So yeah, we want to talk about how we are going to use TDX with different container-related use cases, and really what we're seeing on how we can use TDX in Kubernetes is basically where we're placing the isolation layer that TDX gives us. On one hand, we can use TD to isolate Kubernetes pod themselves. So that's the use case number one, where essentially you would use TDX as a hardware-based isolation layer for each and every pod. That's kind of the Kata containers usage model for those who are familiar with Kata containers extended to TDX. And the second one is basically placing the isolation layer at the worker node level. So you would essentially run a Kubernetes node inside a TDVM. It's more of a classic way of running a worker node today. Today we're doing that with legacy VMs, and the idea would be to extend that to TDX. So if you look at the visual representation of this, use case number one, which is again using TDX as a pod level isolation layer. Each and every pod, if you want it to be so, could run isolated through between each other through TDX, and that is the Kata container model. So what we would do is instead of using VT directly, we would use the TDX APIs exposed by KVM, and place each and every pod inside a TDVM. That's the first use case. The second one, Ravi, is that's the more again classic one where you would run the entire Kubernetes control plane on the node inside a TDVM. So this is essentially what a lot of people do today in either managed infrastructure or private clouds. When they run Kubernetes, they run each and every node usually inside a virtual machine, VT or AMD, doesn't really matter. And here we would just put that inside a TDVM. And the use case that we want to focus on today is use case number one, which is placing a Kubernetes pod inside a TDVM and use TDX as the hardware isolation layer for Kubernetes pod. And the thread model we're trying to implement here is about protecting the container data and code in use and at rest. Protecting it in use means essentially the pod is going to run inside its own dedicated TD. It's not going to share memory with other pods. It's not going to share memory with any other containers. It's just going to have its own private memory, its own dedicated ephemeral key at the pod level. We're also going to protect the code and data at rest, and it's mostly about protecting the container images. And this is one of the biggest challenges that we have to do. We have to fix or address to implement that model. How do we protect container images from being tampered or even being seen by the host in that case? Remember, we're trying to completely remove the host from the pod and from the container TCP. So the first thing we are saying is that the container images should be. Can you take one slide back?
Sorry. Yep.
Sorry. So the first thing we're saying is that the container images should be encrypted or signed, and the host will never ever. The host must not get the decryption keys. So the container images will be in that model would be decrypted and mounted in the guest. And so what the software architecture we're proposing is to offload the Kubernetes container image service inside the guest, and have the agent inside the guest, which is the Kata container agent, running the attestation and getting keys provisioned through the attestation service. And we do that every time we're adding a new container. So if we look at this quickly, step by step, so we have this infrastructure here where we are running on a node. We have kubelets talking to Containerd or Cryo. And we're essentially going to use a dedicated runtime class, a Kubernetes runtime class. And when we create a pod, the Kata shim, which is the Kata container shim layer talking to Containerd, is going to start a new TDVM through KVM. And this TDVM is going to boot up to the Kata agent layer. And here, the very important point is that the entire user space, kernel, and firmware stack is measured and is going to be tested. So everything up to the Kata agent is going to be measured and verified. When we want to add a container to this, we're going to get a request from Kubelet to start a container. And what we're going to do is from the Kata agent, which is again a part of the TCV, the Kata agent is going to request a key from the attestation service, from the key broker, in order to actually decrypt the container image for this specific container. The attestation service is going to send us a challenge, an attestation challenge, and we're going to reply back with a code. And everything again is happening from the Kata agent. So the Kata agent will have the ability to request a code from the C module. Once it sends the code to the attestation service, the attestation service hopefully verifies it and sends a key back and provisioned the TD with the key for this specific container that we're trying to add. Once we get the key, we can decrypt the container inside a TD. So we unpack and mount the container images inside a TD. We're being backed by an ephemeral block device that is going to be as the TD is terminated. And if we need to add more containers to this pod, we're going to go through the same process and basically construct the Kubernetes pod based on a verified and measured software stack, which is, again, everything up to the Kata agent. We only have a few minutes left. And so if we look at the software implication, how we want to implement this, the very interesting thing with that approach is that the container workload itself wouldn't need any changes. So it really is a lift and shift model. You would take your container image and put that inside your TD and build your Kubernetes pod with unmodified container images. The Kata agent will need quite a few changes on the OS and TDVF layers, the firmware and the kernel layers. I think we're looking at exactly the same changes as you would need for a regular TD VM. There's nothing container specific here. The biggest changes are actually happening at the Kata agent layer. And those changes are mostly for the agent to be able to run an offloaded container image service. Again, the Kata agent in that architecture would be responsible for pulling, unpacking, and mounting the container images layers without the host being able to see them. And for that, we need to offload part of the CRI image service in the agent. And the other part of the big Kata container agent modification would be the attestation implementation. So we'd get a quote from the coding enclave that Ravi described a few slides ago. And we'd be talking to the Kata agent, would be talking to the attestation service in order to provision the keys and then decrypt, unpack, and mount the container image layers in the TDVM. Once you get that done, you can actually run a container image, a pod, actually a Kubernetes pod, with a set of container images that you've been getting the right keys from a measured set of from a measured and verified software stack.
Okay.
You want to take it back from here?
Sure. Thanks, Samuel.
Sure.
So Samuel walked you through some of the key touch points. A couple of the links that we had on the previous foil are active issues and PRs that I can post a link for in the chat window, or since it's probably not accessible directly from the presentation. A couple thoughts more also about TDX futures, right? the couple other things we are working on is things like migration that we will start to publish some of the details soon. And also we wanted to like look forward and get feedback from the community on some of the confidential IO capabilities, right? TDX 1.0 is limited to paravirtualized IO only, right? But some of the capabilities that Intel has been working on, I wanted to sort of draw the attention of the community towards that, right? In terms of link encryption, which would be needed to interact with IO devices, right? As we think about IO devices interacting with trusted execution environments, right? And also the ability to extend some of the authentication and attestation parts. I mean, again, we had a lot of discussion about attestation today. There is being a lot of work being done in the community on extending some of these, or creating rather authentication capabilities for devices, right? With and being able to transport them using the SPDM, application protocols, right? That are being discussed, as well as support in PCIe to actually enable devices to report those measurements. And those will become important as we talk about using containers and VMs with devices, etc. in the future, right? So I have a couple of references here to some of the white papers, and just wanted to thank the community for giving us a chance to present this topic here today, and looking forward to some of the discussions, right?
Just, uh, just
Yeah.
one more thing, Ravi. Sorry. If you're interested
Sure.
in the participating and contributing to the effort that we're doing in the Kata Containers community for enabling Kubernetes pod to run through confidential computing technologies. We're enabling all of this for TDX, but also for other confidential computing technologies. This is a cross-industry effort. We have weekly meetings on this one and a bunch of open issues and PR. So please join the discussion and the fun. Thanks.
Just gonna interrupt and say we have some time for you to do questions if you like. We probably like 4 minutes ish. So if you want to stick around, you can answer questions, or if there's anything you rush through, like go like feel free to talk a bit more if you'd like.
Sure, we can maybe take some of the questions from the chat. Again, Jan asked a question: is it possible to create a TDX protected VM from inside a regular VM? Does it introduce hardware-enabled nested virtualization? So Jan, the thought is to have, at least in TDX 1.0, is to essentially support TDs as first-level VMs, right? First-level confidential VMs. We do have some thoughts on how we can enable nested virtualization for TDs, right? So this is the notion of nested VMs running in TDs, but that is something that's sort of being planned for a future capability. So yeah, just let us know, Jan, if we answered your question. Sure. And then Mohammed had a question: what is the expected plan for TDX V1 to be released? So so we are working towards that, Mohammed, right? And you can see some of the efforts that we're putting on the open source for, as Samuel said, for Kata containers, as well as for on the VM side. There is work being done to upstream the changes for KVM, for Linux guest, right? That will run as a TD. So the goal is to put this capability out, in a product soon, right? That's sort of the goal.
To follow up on this one, Ravi, on Kata containers upstream already today, you can use TDX or soon in next week SEV and IBM's encryption technology to run your Kubernetes pods with encrypted memory already. So this is really ongoing at the moment.
Okay. There was also a question from thanks, Sergio. There was also a question from Mark Novak: is there a way to extend confidential computing to peripheral devices such as network and storage offload? So yeah, that's what I was referring to. Some of these upcoming PCI SIG and SPDM DMTF standard proposals, Mark, that they give us sort of the framework to think about being able to authenticate devices and connect them securely to the SoC, right? By protecting the link, especially for discrete devices, right? And that is only part of the framework, though, right? Once you have those capabilities in place, you need some additional platform support that we hope to extend through the TDX capability, so that you can also, provide those devices and be able to use those functions and accelerators directly from the TD, right? And not have to require, copying data in and out of the, trusted environment, right? So that's sort of the goal, Mark. So hopefully that answered that question. Any other thoughts, comments, questions? Yeah, and we agree that for some of the really performant models of trusted execution and confidential compute, we need that sort of performant models for attaching the trusted execution environments to devices and accelerators. Okay.
All right, well, thank you very much to Ravi and Samuel for the presentation. From here, we will transition to our next speaker,